Hi, my name is Joris Kaal. Thanks for having me. I'm very happy and thankful to be here. Thanks for being in this room and not choosing to be in another room. As I said, my name is Joris Kaal. I am an organ-on-chip research engineer at CEA Leti, which is the largest research and technology organization in France. And today I would like to present to you how, based on demands that we saw in industry and in-house, we developed a system to rapid prototype and produce at semi-scale ISO-conform organ-on-chip devices. So I think we've all seen that there's a first generation of commercial organs on chip on the market. If you're a biologist, you can choose to use javelin or mimetas or tissues, anything you like. But as we see as well is that there's still, well, this conference is a proof of it, there's still a huge development effort to be made because there's still things to be improved. So if there's still things to be improved, what are the things that are missing? What demands do we have as a community on our organ-on-chip devices? I hope I won't be kicking in too many open doors here, but in the beginning, we of course want to rapid prototype. We want to think up a design, we want to make it and then test it. And these tests, we would like them to be reproducible within our lab. Therefore, we want our chips to be reproducible, we would like our materials to be reproducible, and we would like our processes to be reproducible. As soon as we have a test or an experiment that works in-house, we might want to compare or benchmark to other laboratories or other companies. So there's some kind of comparability that's necessary. And then finally, of course, among all the prototypes that we're all making here, all the tests that we're doing, there might be some chips that we want to industrialize. Say, for example, we find a benchmark that clinicians can use for treatment selection or pharma could use for phenotypic screening. We want to produce them at a larger scale. So we want to anticipate this industrialization in our chip designs. Now, to facilitate all this, it might be a good idea to standardize some things. I think you might have heard about that on the conference this week. As, for example, Donna Mendrick said in her keynote Wednesday, it's important for us to control our source materials, it's important for us to control our manufacturing processes because our biological products can be very sensitive to these aspects. And apart from materials and processes, of course, it might be a good idea to have some design guidelines for the shapes and the designs of our chips. Now this is where, as I showed here, ISO comes in, MFMET comes in, CSB comes in. They are trying to define guidelines that can, they're trying to define guidelines for our microfluidic designs. Notably, the ISO norm 22916 that came out last year, which is, let's say, an important product of this effort. So, these are the demands. Quick sidestep to what this ISO norm means or contains. There are three important parts. For your card dimensions, you can use microscope slide dimensions, credit card size dimensions, or micro well plate dimensions. If you want to put connections, fluidic connections on your cards, you put them on a 1.5 millimeter by 1.5 millimeter grid. If it be lures, mini lures, fluidic circuit board connections, anything you like, you put them on a point on this grid and you should be fine. And last aspect, if you want to create a building block, for example, for a fluidic circuit board, as Andries van der Meer pointed out in his talk on Wednesday, the only rule is that you make them a multiple of 15 by 15 millimeters. So 15 by 30, etc. So that's the ISO norm and the demands that we found. And the funny thing, it's not very funny, but the funny thing is that inside CEA, we found that we had these same demands that we saw in industry. We're quite a big organization. We're 16,000 people with a lot of different research groups that are working on a lot of different projects, but also on organs on chips. And me personally, Joris, I'm in a research platform for the integration, surface functionalization, and microfabrication, which is a very long name to say that if you need an organ on chip, we are the ones that can develop it for you. That's the point. And only for organ on chips in-house, we've had to reply to about 20 demands, 19, 20 this year, for chip designs. And therefore, me and my platform colleagues, we started to pose ourselves the question, how can we respond to these demands? Now, this is where I'm going to get to the point. This is our response to this demand. We developed a system, a hot embossing system, that allows us to rapid prototype and produce at semi-scale, ISO-conform, reproducible organs on chips. Now, what does that contain? This is what it looks like. On your left, you see a standardized mold bottom, a hot embossing mold bottom. And on your right, you see a variable insert into which we can micro-machine the microstructure that you would like to have in your chip. Just a quick explanation of what hot embossing is. For those of you who aren't aware, it's an extremely reproducible manufacturing method. And we've chosen to use with thermoplastics such as COC, PS, PMMA, etc., which are, and silicon, by the way, which are extremely or very stable materials. So how does it work? You take this mold bottom, and in all these 12 holes, you can put a little virgin piece of plastic. Then you take your insert with your microstructure, you put it onto the mold, and you start to heat that all up. You heat it all up above the glass temperature of your plastic, which makes it moldable, makes it a bit soft. And then you come and you press really hard onto your insert into your plastic. This way, transferring the microstructure from the insert into your piece of plastic, which is now a microfluidic chip. The idea of the system is that this bottom, it always stays the same. You always use the 12-hole bottom. And, well, this is our 15 by 15 millimeter mold, by the way. You can take any size I just mentioned in the ISO norm. So this one always stays the same. The insert is where you get the possibility to either rapid prototype or produce at semi-scale. If you rapid prototype, you only make one insert, you make it quick, takes a couple of hours, you start making some chips, etc. If, however, you found a design that you like, you make an insert with 12 inserts, and you start profiting from the entire mold bottom. So, how do our research teams at CEA work with this? There are 4 steps. Step 1, you decide that you want to make an organ on chip. You choose your building block, you choose your dimension, and either, for example, in discussion with me or with my platform colleagues or by yourself. And in-house, we have a SolidWorks library where you can just pick and slide the standardized building block into your SolidWorks to get going. Next step is you choose your connections. And again, we have a SolidWorks library where you can slide in your connections, and voila, you add them onto your chip, and you're ready to go. For example, if you choose one insert and one entrance and one exit, you're good to go. So as soon as you've done that, you can start designing your microstructure on the other side of your chip, and then you can do whatever you want. So there's some standardized basis that you can put in place really quickly, and then you're free to go. So, for example, one of the organ on chip designs that we have. So, you have your chip designed, you got your basic design down, and then you give it to us, me, and we turn it into an insert design. You see here. This insert we can use with the system to create some chips. The chips you make, you get them going to your biologists, they can test it, they can see, some things to be improved, we can adapt the design, remachine and insert quite quickly, then again make some chips and start iterating with your biologists and see if there are some things to be improved. Until at some point, for example at your 3rd iteration, just a random number, you get to a design where you think, okay, cool, this works for my biologists, this works for everything around the team of biologists. I would now like to do some more experiments. I'd like to start using it. I would like to start testing some more circumstances, some more substances. I need more chips. And that's when you transfer to a 12 insert design, and you can start making 12 chips at a time, this way producing at semi-scale. After that, if you'd like, we've got partnerships in place with industrials that can go to actual large-scale production. So yeah. So this is how we in-house at CEA, we work, and we're able to create any organ-on-chip design that we would like. So what can we make with this? Like I said, anything you like. There's no really any limit. But what have we made with this? What's in, let's say, the CEA catalog of chips? These are just some examples. Of course, we can make organs on chips. As you see here, for example, is a pancreas on chip. It's a chip that we use to vascularize spheroids. And we got this chip in silicon as well, where the microstructure is made out of silicon. And it's then integrated onto your building block, which can either be COC. For us, it's generally COC, like Murad mentioned, it's quite a, let's say, pleasant material. But you can use PS, PC, like I said. So we got some heterogeneous integration going on in this chip. We've got some other organ-on-chip design. This one is for a biopsy. You can put a little biopsy in the little chambers over there. Apart from organs-on-chips, I think it's quite a common thing as well. We can integrate microfluidic functional units as well. So what we noticed is that quite a lot of projects would like to have a filter unit, or would like to filter at some point in their protocols. And we thought, okay, let's make one building block that we can use for all these projects. However, they didn't want to use the same building blocks. Oh, sorry, they didn't want to use the same filters. So we created a building block that's, let's say, standard, into which you can integrate any 30 millimeter filter that you can buy at Merck or Sigma Aldrich or whatever. So we got functional units, and then finally, if you want to, for example, trace the viability of your organ on chip, or maybe track some kind of excretions, we can do some sensor integration as well, such as this impedance and oxygen sensor, which we use as well to test the difference in oxygenation between PDMS and COC. So these are some examples of what we've made. And then finally, well, not entirely finally, but a thing that I would like to point out, any chip that we make with this system, you can choose how you use it. If you choose to have lure connections, you can hook it up with your mini lures, with your tubings, hook it up onto a syringe pump, a fluogen pump, anything you like, and you can use it standalone. At the same time, if you want to be more compatible with the whole well plates format, you can use fluidic circuit board connectors and have a fluidic circuit board in your well plate size, onto which you can attach your building blocks. For example, to parallelize, or maybe to put some things in series. You can have your organ on chip in the first one, a filter unit for some excretions or extracellular vesicles to filter, and then have a sensor in your third building block in a series. So there's two options, either standalone or fluidic circuit board, and any chip that comes out of your system, you can choose how you want to use it. So, to sum up, we saw in industry and in-house that there's a large need to rapid prototype chips that are reproducible, that are comparable, and we want to anticipate a possibility of industrialization. And to facilitate all that, we would like to comply to some standards that are put in place. To reply to these demands, we've created a system that allows us to rapid prototype and produce at semi-scale isoconform organs on chips. And this now allows us to create any kind of microfluidic building block or organ on chip that we'd like. When I say we, I would like to thank some people, because I did not do this alone. I would like to thank all my colleagues, notably the microfabrication team, because there are some real wizards in microfabrication there, but also all the biologists we have in-house that we can, I was going to say we can use, but no, but that we can cooperate with to develop these organs on chips. We got silicon experts, we got microfluidic experts. There's a lot of people that helped in putting this into place, so I'd really like to thank them very much. So what we, as let's say a team, saw is that this gave us a big gain in rapidity, in compatibility, and in costs. So we'd be very happy to, or me personally, or we as a team, would be very happy to collaborate with anyone that wants to advance organs on chips. So feel free to reach out, to pose a question. Don't hesitate to contact Jean de Boisson, who's our industrial partnership manager. So yeah, with that, I would like to thank you very much for your attention, and I would be happy to take any questions you have.
Thank you very much, Joris. We have one question here.
Yeah, thank you for the nice talk. A really cool technology. One question, how high can the channels be that you can hot emboss with the technology?
I'm sorry, I did not...
So what is the channel height you can make with the technology?
Channel height? Well, we're not very limited. I think the deepest we've made so far is 1 millimeter. 1 millimeter? Yeah, which starts to enter into the discussion, is it microfluidics or not? No. But in general, we're in several hundreds of microns.
Yeah, okay. And the aspect ratio you can make?
The aspect ratio, the biggest that we have experience with is 2:1. So you can make a pillar, for example, with a diameter of 100 with a height of 200. We've tested a bit higher. We need to still develop to put that in place, but that's where we are now.
And the surface quality, can you then thermal bond the chips, or how do you then later seal the chips?
The question was if we can thermally
no, if you can, yeah. How do you bond the chips when you kind of made them?
I'm really having trouble hearing the...
How do you put everything together? How do you bond?
You mean onto a circuit board, or if you have multiple layers in your chip?
Yeah.
Onto a circuit board, we got clamps, either magnets or screws or actual clipping clamps. If you want to do multi-layer, like a building block with multiple layers, for example, we have in place a method of thermally bonding multiple layers of COC.
Okay. Yeah. Thank you.
Thank you very much.
Okay, thank you very much. I was just wondering, you prepare the mold with the CNC milling, or you do other techniques?
We prepare the mold how, sorry?
The stamps that you are preparing to do then the shaping.
Yeah.
So they are produced with CNC milling?
Yeah, yes they are. They're micro machines.
A very nice talk. I'm wondering, is there any standard for the heat toxin or intoxin percentage for this type of thermoplastic and the ISO standards?
Is there any standard for what, sorry?
For the heat toxin, intoxin levels in the materials for the microfluidic or organ chip application.
You mean if there's any standards for the chips in dimension or in the structure that you make?
The toxic, intoxin or heat toxin, yeah. No, toxicity.
Toxicity. Pardon? You mean for the toxicity of the material?
No. Because for cell culture, the toxin level or intoxin level or heat toxin level should be very small. I mean, it should be compatible with the cells. Is there any standard I can follow? I mean,
If there's
to
a
use
standard for the toxicity of the material of your chip?
Yes, yeah.
Not that I'm aware of, but I do think they're putting them in place. For example, the MFMed project, they're developing protocols to test your chips.
Mhm.
There's a focus group for organs on chips as well that's going to look into, let's say, standards for anything that's applied to organs on chips. So I think that could be one of the things they will look into. But as of now, I don't think there's any standard in place, not that I know of.
Okay, thank you.
No worries.
Let's thank Joris again.